Hello and welcome to our first video in this course. Today we want to talk about chapter 2 of our lecture notes, which you can, as always, find online following the link. And today we want to talk about the preliminaries, which we need to cover before we can even begin to learn about data science or about R. So today we want to install R, also install RStudio, which is a really convenient tool to work with R. And also we want to install and cover a few basics about the version control system Git, which is really helpful if you want to work together with others and to collaborate on an open source project. So it's really neat to learn it. And this is why we also will use it in this course, so you can work in teams to solve a few exercises. Okay, so let's get started right away. First of all, we need to download R, so the language itself, which means that we can follow this link here to the CRAN, the Comprehensive R Archive Network, where we can download R for our operating system. So for me, I would have to follow the link here to download it for Windows. Once you have downloaded it, you can just install it the way you install any program on your computer. It's really straightforward. And once you have done that, I highly recommend that you go to the RStudio homepage and also install RStudio. So you go onto the homepage, click on RStudio Desktop, and then you download RStudio Desktop, which will where you can download it for free here. And once you've done that, you're basically all set to start working with R. If you're using Windows, then it may help you to also download the R Tools program, which I have kind of hidden here in the footnote. So if you follow that link, you will end up on this homepage where you can download it here. You don't necessarily need that in the beginning, I think. But sometimes you can run into problems installing packages. This may not happen right away, but if you use R a lot, then you might run into problems there. So it just helps to have it installed. You don't need to install it right away, as I said, but if you run into problems installing a package, which we will cover in a second what that is, then just keep that in the back of your mind that you can maybe install it. So just a reminder, this is only for Windows. On other operating systems you don't need that at all. Okay, if you've installed RStudio then as well, then you can open it, which will look something like this if you open it out of the box. If I open it, then it will look like this. So I have adjusted the theme, so the appearance of RStudio a bit. And if you want to do that too, you can just go to Tools, and there you will find a drop-down menu once you click on this here, and there you go on to Global Options, and there you can change to a different theme if you want. So here I basically chose a darker theme, which personally I think is nicer, but you can go with whatever theme you desire. Okay, so here we have 3 large panes. So here you have the console where you can type in stuff. Here I will kind of throw an error saying whatever I typed in there I didn't. He doesn't know, so you should kind of try to only write the commands that R can actually handle. Here you will find an environment, which we will talk about once we declare variables. And here you can find files. So this will show you your files, and a few other a few other tabs you can use, and which we will see, which will become useful later on. Okay, so as I said, sometimes we'll need to install packages. What packages are is basically a bunch of functions R can understand and a few data sets bundled together into one package and made available to everyone using R. So if we, for instance, want to install one of my favorite packages, we will or if you want to install any package, you will just use the command install packages. As you can see, R already tried to guess what I'm trying to type, and if I'm pressing enter, then I can autofill it. And if I kind of want to install one of my favorite packages, then I will just have to give the name of that package, which is praise. I will have to put it into quotation marks here, that you will have to be careful about this. And if you hit enter, then it's downloading and installing that package. And now I can use all of the functions and all of the data sets that are inside of that package. But before I can use it, for instance, the function praise is within this package. If I try to execute this now, then it will throw an error again saying it doesn't know what the function praise is. So we will have to tell R that we want to use the praise function from the package praise. And we do this by, as you see, R is already guessing, okay, maybe you want to try a function from the praise package. These two double points will mean, okay, this is a function from the praise package, and then you can run the package praise. So this will just give me a few compliments, which is, well, nice. If you are in a bad mood, maybe this will help you. In any case, as you see, it might be annoying to always write the package name here in front. Would be neat if we can just write praise here without having to specify the name of the package every time I want to use one function. And we can do it if we tell R at some point that we will use this package all the time. So what we do is we use the function library and tell it to attach or load the package praise. This will execute, and now I can use praise again without having to specify the the package name. But this also just generated a warning message, which we really don't have to worry about. It's just that my R version is not completely up to date, so this might sometimes cause issues, but in this case it doesn't really matter at all. Okay, so this is how you install packages. And what we need to install right away, I mean, praise is a nice package, but it's not really functional in the sense that it gives us a lot of helpful functions. But a different package which you should install and which we'll use throughout this course is the Tidyverse package. So we will need to install it. So by the same approach as we did last time, we'll just write install packages and then Tidyverse. This is the name of the package we want to install within or between quotation marks. And we'll not execute this now because then this package is quite big, so it will install a lot. So I will just load it instead because I've already installed it and I only need to install it once, and then I can always attach it. Whenever I restart R, I need to attach it again, or I need to load it via library. So here I can load it. This will take maybe a second or two. And then again, it generated the warning messages. Ignore those. But what it also did was giving us a few information about what packages it attached, or attaching and loading is kind of the same thing. So don't worry about that word. So it said here that it attached 8 packages. So first what we learn is that the Tidyverse is not actually just one package, but it is a collection of a lot of packages. All of these packages are kind of structured in a similar way, and they use a lot of the similar syntax, so they can kind of work together really well. And all of these really good functions or great functions form what we call, or what is called, the Tidyverse. So it's a whole world of functions or of packages, and each package is tailored to a specific task. For instance, as you can see here, there is this package ggplot2, which is the graphing package of the Tidyverse. So we can create a lot of really cool figures and generate a lot of plots, which we will do in the next chapter. So in the next video we'll do it. But the task of generating plots is really what ggplot2 does. Similarly, there are other packages. So Tibble is basically a set of data. R usually use data frames, so it's just a table of data. So Tibbles are handling our data. Reader, for example, is if you want to read, if you have a data set on your computer and you want to load it into R, then Reader is the package that has a lot of functions that can handle a lot of data types and can get your data into our workspace, and so on. And there are a lot of different packages. I don't want to deal with all of those, but as I said, the Tidyverse contains really a lot of different packages which we will need. What the message from the library call also shows is the conflicts information. So here it says that dplyr, which is just this package here, has a function which is called filter. But our package stats, which is automatically loaded with R every time we start it, also has a function filter. So because R cannot handle two functions with the same name at the same time, then the last function that was loaded will override the previous version. So now if I want to use filter from the dplyr package, then I can just write filter. Okay, I cannot really use it because I don't have anything to use it on. But if I want to use the other filter functions, then I kind of have to use the full name again. So I will have to write stats, filter, and so on. That's basically it. And yeah, that's basically the information we have in here. Okay, so let's get you equipped with a couple of commands you should use. So what can R do? R can basically function as your standard calculator. You just type in whatever you fancy, just 25 times 140. And this will, every time you hit enter, you execute the code, and then you will get the result. It can do a lot more. So, for instance, if I want to compute the square root of something, square root of 4 should be 2, and R will compute it for us. I can compute the sine of something, sine of pi. So if I want to use pi, I just write out pi in R. That's of course sin. So the command for the sine is just sin. And here you see that it should actually equal 0, but it doesn't. That's an issue we have with floating points, and we should be aware. With decimal numbers, this is an issue we run into whenever we use computers. This is something we should be aware of, but not something we can really do much about. So just keep it in mind that sometimes there is instead of 0, you will get a really small number. In a lot of cases, this won't do any damage, but sometimes in a few calculations it might. But in our cases, I think it shouldn't be any problem. Okay, so in the lecture notes, you will find a lot of other commands you can use, for instance, cosine or whatever. I don't really want to show you all of them. You can just look into the lecture notes and then apply them yourself. It's not really a big deal. So instead of new functions, let's talk about variables. As I said, we have an environment here, which will always list our variables we save. For instance, if we want to save the square root of something, then we can just write square root. So we write the square root. This will be our variable name. Then we'll have to draw an arrow, and then we write, I don't know, square root of 155. This is what a value we need later on for whatever reasons. We can execute it, and you see we don't have an output here. All we have is just the line we wrote, but instead we can see that in our environment the square root variable we named is in there now. So if I want to see what value I get, I can just write out the name and execute it, and then I will see, okay, the square root of 155 apparently is approximately 12.5 or 12.44. Yeah, so as I said, there is no output, and we can generate an output with just writing out the variable. Sometimes if you don't really want to declare a variable and then write out the name itself, you want to save and print, then you can just take the call and put it into parentheses, so the declaration. And then it will both save. We won't see this now. Let's just clear our environment here. So our environment is empty again. And if I press this now, then the variable is declared and also its value is printed, which can be helpful. And sometimes you only want to show a variable's value you have already computed way before. So then in these cases you can use the print function, which just prints you whatever you throw into it. Then a small note onto the variable declaration. And first it may feel, especially if you've already some programming experience with other languages, it may feel weird that we use this arrow. First of all, it's weird to write it like this. So if I type type the characters, it's a pain. RStudio has a neat shortcut which uses the Alt tab and the minus. Then I can generate it with one shortcut. But the real issue here is that we can also do the same thing with an equal sign. So instead we could write sqrt of the square root of 155, can declare it into this variable here using an equal sign. It's totally valid, and that's usually the standard in other programming languages. In R, it's usually discouraged to use it for declaration because often we use the equal sign also within a function. So this is why usually we try to differentiate between a variable declaration and using an argument of a function. We will see later on what I mean, but this is the reason why usually it's encouraged to use the arrow instead of the equal sign. So this is why usually I will always declare things, variables with this. And if you're using RStudio, it's basically really easy to write the arrow with the shortcut. Okay, so let's move on to more complicated variables. Let's declare vectors. So in R is very known for its vectorized calculations, same as MATLAB if you've used it before. If not, don't worry about it. Basically, a lot of computations can be done using vectors. So instead of just looking at one number, I can, for instance, save two numbers into a vector. As you see, my output now is a vector of 2. And if I save this, for instance, I can also save vectors into a variable here. And all we need to do is throw it into the C function. This is actually a function which gives us a column vector, and we can make it arbitrarily large. And we can also save other stuff. We don't need to necessarily save numbers. We could also save texts. So for instance, if I want to write, I don't know, in the lecture notes I wrote Alibaba. So I can also, as you see, I can also save a vector full of characters. So a character is a data type for, well, characters. And yeah, you can kind of save them easily. You don't necessarily have to use numbers. What you have to look out for, if you want to call this, if you call this vector now, then you will see that there are quotation marks around the entries of this vector. This indicates that these are strings, that this is a character, and sometimes you will have numbers disguised as characters. So for instance, if I throw in a 1 here, say I want to save both numbers and a character, so 1001 for instance, and if I call this now, then I will see that around my 1001 there are also quotation marks. This means that this entry here is now saved not as a number but as a character. This is something you will have to look out for. So what you learn from this is that R, if you use a vector, will always convert it to the same data type. So since Alibaba cannot be a numeric data type, as you see here, it will have to convert the 1001 to a number, to a string. Yeah, that's basically what you have to watch out for, especially if you have a vector full of numbers, but they are actually saved as characters. This will cause a lot of confusion, so just look out for this. Alright. I don't want to go into that much details about data types. It's summarized, or there's a list of data types R uses in the lecture notes. You should look at this because in the later chapters I will use these words of the data types to describe different data types, but here I don't kind of want to go into that much details. A different thing here is, so what we used is vectors now, they are all atomic. Atomic means that, as I said, they are always, the entries are always of the same data type. If you want to have something else, if you want to mix data types, then you will need something which is called a list. So there you could, for instance, combine a vector of characters, and then you can throw in a vector of numbers and throw that all into a list. Then it will show you, oops, I missed an S here. Then it will give you something of a list. So the first list entry is this whole vector, and the next list entry is the second whole vector. And as you can see here, there are no quotation marks here. So this is actually saved as a numeric variable and not as a character. For now, just know that there are lists and they are very powerful, and we will use them later on in the lecture notes. But here, this is just to make you aware of the different structures you can create using data types in R. Okay, so let's cover a few more convenient functions you need. For instance, if you want to create an empty vector, you can just, for instance, you want to have a numeric vector, then you will just give the mode as numeric, and if you want to have a vector of length 3, then you will just give that argument and say that it's 3. So this is what I meant earlier when I said we want to use equal signs for the arguments of a functions, as in here, and we want to use the arrow for declarations of a variable. This is where we try to differentiate between these two things, and this is the syntax I adhere to. Okay, so as I said, we can create an empty vector basically by a vector. We could do it with a different data type. We could also say logical, which is a data type, so it's true or false. Yeah, we could do that too. And there are usually a few shortcuts. For instance, if you want to create a numerical empty vector, you can just call numeric 3, and this will generate the same thing as above, but this is just a shortcut for it. Okay, so again, we need to cover a few functions before we can learn more interesting things. So let's talk about sequences. Basically, if I want to compute or generate a vector, for instance, of even numbers, then I could manually write them down, which is really tedious. But instead, I could also use the sequence function, which basically has a few arguments. One of them is the from argument. So to create the previous vector, we start at 2. So from to 10, we want to go to 10. And we want to go by increments of 2. So this will create the vector I just created by hand. And of course, we could generalize this to any other number, whatever, and this will create the vector we want. And as I said, again, there are shortcuts here too. So for instance, if I leave out the by argument, then by default, it will just assume, R will assume by default that the by argument is 1, and then it will just use increments of 1. And if I want to have a shortcut for this, I can just go to double point and then to 24. But what is important to know is that, of course, I know the functions by now, so the sequence function, I know how it works. But if you don't know it, you can always look into the documentation, which you can either do by calling question mark sequence. This will then open the help tab here, or you can always write sequence if you're using RStudio and press F1. Then it will also open this page here, and this opens the documentation for this function, and basically it explains the standard notation here, and it says here, well, the first argument is always from, the second argument is to, and the third argument we don't necessarily have to compute, because it can compute it on its own by the to and the from. And what this also helps us with is that we don't actually need to write out the arguments. So the documentation tells us that the first argument is always from and the second argument is always to. So instead of writing this out every time, we can just write 2 to, for instance, 12, and it will, R will understand that you meant, well, the first argument needs to be 2 and the second argument needs to be 12. So this is how R works, and you can always find the standard notation in the documentation, which is really messy at first. I won't lie, you will need some time to get used to it, but once you do, you can actually find a lot of information in here. There's more information about the arguments, and usually down below you will find examples, which sometimes helps to start with. I mean, if you have a new function, maybe just look at a few examples and see how it works, and then extrapolate from that how the function really works. You don't necessarily have to read everything that is written in here. Okay, so one more function. I really try to make this brief here. I know it's not the most exciting thing to just learn one function over another. Is the rep function, which just repeats values. So for instance, I want to repeat the value 1.5 for 4 times. Then I can call this, and I have generated another vector again. And as before, we can leave out the argument's name. This will then generate more vectors. And the rep function also works with vectors itself, so we can repeat a full vector again. Or if we don't want to use the times argument, we can also use the each argument, which is explained in here. As I said, sometimes you have to look for it, because here you won't find it. It's actually hidden in those dots in here. And the dots say, well, you can use each here too, and this is where it's explained. And here it's the vector in here is recycled again, but this time first 4 times the first entry and then 4 times the second entry. Okay, one last thing we have to cover with vectors is the sequence along function. So for instance, let's create a vector of whatever, just repeat 1 10 times, then x looks as we expected, just 10 once. And now we want to compute the sequence along x. Which this does is give us the sequence, so basically the indices of the vectors, of the previous vector. So this just helps us to, if we want to, for instance, later on, if we cover for loops, to loop through all values within a vector, then the sequence along function just gives us the sequence we need to go through. And often you will use this, and this is because this is a safer function than using the length itself. For instance, you could think about, well, you can generate this entry here by yourself. If you know the length function, which just gives you 10, then you could just go 1 to the length of x, which generates what we want. The problem is if, for instance, x is an empty vector, which sometimes can happen by accident if you don't, if you're not careful with your programming, then sequence along will do the right thing and say, well, I can't do a sequence along an empty vector, it's just an empty thing again, but 1 to the length of x will just give you the sequence from 1 to 0, which is often not what you want, so you have to be careful about it. Okay, this is, I think, the minimum amount of functions we need to cover. So let's move on to something which I personally think is really nice in R, or part of the Tidyverse, because it helps you to really think about what you're trying to do. What I'm talking about is piping. So for instance, the piping operator is given like so, and this comes with the Tidyverse. In the lecture notes I've described in more detail which package this is coming from, but that's not important right now. What this does is this operator takes the output from one function we ran before, so say function 1, we ran function 1, and then it uses the output and passes it to the next function, so function 2. Of course, this won't do anything here because it's not valid syntax for R, but let's just go through a simple example. For instance, I will just copy this from the lecture notes. So we have a vector x here, and say we want to compute the maximum of x, which in this case is 12, and then generate a sequence of all even integers from of all integers up to 12, or the first 12 integers, and then compute the sum of it, the sum of the even integers. So we could, for instance, go to compute the maximum first. That's what you often do in other programming languages. You compute first the maximum. This is what we need first. All right, I've got that saved. Now I want to generate the I want to compute the sum of the first 12 integers. So I need to generate a sequence from starting at 2 of increments by 2, and then the length out argument. So I need to get m vectors at the end, or m numbers, should be m. This will be the numbers I need to sum over. So let's just call this the even integers. And now what I said is I want to compute the sum of all those functions, which I can do using the sum functions. And then I got my result of 156. That's what you do in a lot of programming languages, which is fine, but at the end, we really only care about the result. We don't really need to save a variable here just because we need it later on. I mean, it's kind of hard to come up with variable names for each little step. And so instead, in other languages, sometimes you just nest the functions all together. So sometimes you just put it all together. So instead of computing the maximum first and then putting it into the sequence function and then summing it, you just do it all in one line. You have the sum of the sequence, and then in the sequence you use the maximum here. Of course, this will give the same result, but now you will have to read this from the inside. In here, first you have to figure out where is the inside, or where is the starting point, and then you have to read it inside out and figure out from there what this function does. And one elegant way is the pipe, as I said before, because it can help us solve both problems. If I can just take a function, throw it to the next function, and so on, and just at the end generate the result of all the computations, then I don't have to nest my functions, so I have one really long line, and I don't have to save variables in between. So this is what this piping operator can do, which the Tidyverse brings us. So for instance, in this case, we could use x, which is our vector, then give it to the maximum function. This will give us the maximum, and then we could just go on. We could just say, okay, now here why this works is because the maximum is it's clear. The maximum knows how to deal with the input, because the first argument of maximum is just a numeric vector, and the maximum over that is computed then. So here we didn't even have to specify, okay, how does the next function have to use the previous output. In the next step, the sequence function won't know how to deal with this with the output of the maximum. So here we'll have to tell the sequence function where exactly to use the input. This is done via a dot operator. So instead, here we could have written dot. So the function now knows, okay, take the previous output and put it where the dot is. As I said, for the maximum we don't need it, but for the sequence we will. So here we say, okay, for the length out, use the dot, and this will give us the sequence we had before. And in the last step, we could just compute the sum over it, and this is the result. So again, we get obviously the same result, but we don't have to nest the functions now, and we don't have to save anything in between, which is really neat. And you could also write this in multiple lines. So you can write each step into one line, and from that you could see even better what is done step by step. You don't have to write it all in one line, but for each step you could generate a new line, and this way you have a really good overview over your code. So this is why I like it a lot. Okay, and this is why I recommend using the pipe a lot. But as you see, if you want to write everything into one new line, it's kind of annoying that you, if you want to see, I have put an error in there. So I have to start all over again. I have to go all the way back to this line, then write this, and this will be annoying. So what we do instead is we could, for instance, write a script. So if you click on here, you will find a drop-down menu, and you can, for instance, create a script. This will open up a new pane, and basically, instead of using the console, you can just write all your code into a script and then perform all all the functions sequentially by executing the whole script. So, for instance, our previous call I could have written like so, and then I could have just clicked here to run the script, and in the console I will see the result of my calculations. If I'm using R RStudio as I'm doing right now, then I could also press Control and Enter, and then I won't even have to click on here. And for instance, if I have another line of code here, then I could, with Control and Enter, I can go line by line, or I can give all the outputs. If I source the whole thing, then as you can see, it will go through the whole script and execute everything. And if you want to use a short key again, then you can press Control. I don't know what the English word is for that button. Basically, what you press to get a capital letter, you press those two and then Enter. In German it would be Umschalt. I don't know what it is in English. In any case, I think you will figure it out. So this is how script works, and this is something which is really helpful to save code, of course, because everything you write into the console is lost once you close RStudio. So you can save your code or send it to others in scripts. And what you can also do, instead of using a script, you could use an R notebook here. This opens a document like this, and as you see, there are parts where there's real text in here. This is just regular text. Someone has written something, and then there are chunks of codes. So for instance, here I could execute this code again using Control Enter, and then instead of printing the output into the console, as you can see, well, it's still there, but it's not open. What you see, the result, you will always get below the chunk. For instance, if I write 2 + 2 here, then my result will be displayed here. And this is something which I personally enjoy a lot, because it kind of helps to mix both text and code. So for instance, I could, if I'm looking at a data set and I have no clue what the data is about, I can just, or what I even want to try to find there, I can just document all my thoughts in here. So I could say, okay, let's take a look at the data. Then I just write some code here that reads the data in. And then I could write, wow, I have seen whatever. And then I can throw in another chunk of code and do a new operation, whatever. Fancy stuff here. And this way I can, when I try to find something out, I can structure my thoughts, and I can, for what's more important, if I have to leave my work have to do something else and I have to, I don't know, ignore it for a week or two, I can later come back and see, this is what I did there, and I'm up to speed faster. So this is why I personally prefer to use R notebooks, but of course it's completely legitimate to also use something else. So use scripts to save your code. What's also nice is that you can, if I for instance write preview, or I have to save this here, if you press the preview button, then you can also generate a new notebook really fast. So here in the viewer pane you will see there's the text I've written, here's the code chunks, and here's the text again. So I can generate a notebook, as the name says, by just clicking to preview. This will generate an HTML file. If you want to get PDF, you just have to write click knit to PDF. There's even an option to knit to Word, and this way you can generate reports on your data analysis really easily, which is why I, as I said, prefer to use notebooks instead of scripts. All right. this is what I wanted to cover about really the basics of how to work with RStudio. As you've seen probably already, it's really helpful to work with the shortcuts. So for instance, instead of writing this here to generate a chunk, or copy and pasting it, or having to press insert here, you can also use shortcuts. In this case it's Control Alternative I, these 3 buttons, and then it will generate a chunk, which helps a lot. And also the pipe generator, I think I've missed to say that this was the Umschalt thing. So the capital letter button, so Control, capital letter, and M will generate the pipe, and so this way I can work really fast. And this is one of a lot of advantages using RStudio, because the short keys help you to program more efficiently. Okay, one more note before I close this video. In the next video I will talk about Git then. It's just so that we can so that it's split according to the topic. So this video will cover the R basics and the next video will cover the Git, but it's basically one unit. One more thing is that if you save your code, then you can of course send it to others, and if you do, it's really helpful if your code is legible. And what you can do to make your code more legible is to adhere to a nice style guide. So this is why I personally prefer the Tidyverse style guide. I have put it into the lecture note. If you follow that link, then you will get to this homepage, and you can see there's it's a whole book on what's proper style encoding and what not. It's not a lot of text here, and there are a lot of examples, and I really suggest that you take a look at it, because it really helps you in the long run if you have a legible code. So I will just leave you with this, and I'll see you in the next video on Git.